All right, so page 347, number 14, says Adam drops a ball from a height of 12 feet. Each bounce is 50% as high as the previous bounce. What is the total vertical distance the ball has traveled when it hits the ground for the fourth time? And then they give us a graph there, right? And you can see that the graph starts when x is 0, y is at 12, because he's dropping it from 12 feet, a height of 12 feet. And then it bounces at when x equals 1, it's 0. Then it bounces back up to 6. Then when x equals 2, it's at 0. Then it bounces back up to 3. When x equals 3, it's at 0. And then it bounces back up to 1.5, right? So when he drops it, in fact, let me sort of just draw this because it might be. So 3, 6, 9, 12. So whenever he drops it from 12, it comes down and bounces, and then it goes back up to 6, and then comes down and bounces. Then it goes up to 3 and comes down, and then it goes just 1.5. And each of these is an x. So that's 1, 2, 3, 4. All right. So we need to find the total distance the ball has traveled when it hits the ground for the fourth time. So how do I want to do this? This first piece right here would obviously be 12 feet, right down to the ground. Then the second piece right here would be up 6, so we'll say plus 6. Then the ball travels another 6 feet back down to the ground, so plus 6 again. Then it travels up 3 feet, so plus 3. Then back down to the ground 3 feet. Then it travels up 1.5 feet. And then it travels back down to the ground another 1.5 feet. Right? And so what we're seeing is this is very much a geometric series because the terms of the sequence are being multiplied by 1/2 every time, and we're adding them all up. So let's see, 12 and 12 is 24, and 6 is 30, and 3, so 33 total feet traveled by that ball. All right, so we're taking a look at number 28, and we need to be able to read sigma notation right here. That means the sum of the first 6 terms of this geometric sequence. And what they're doing here is they're giving you the explicit formula of that geometric sequence. So from this explicit formula, we can get a sub 1 right there. Remember, let me jot this up here. Explicit formula, a sub n equals a sub 1 times r raised to the n minus 1. Well, that's what they're doing. The 4 is the a sub 1, so we know a sub 1 equals 4. And r, the common ratio, is 2, so r equals 2. So you have to be able to pull that information from reading the math, right? Now, we're going to use the formula for a geometric series, which says, let's use some blue, s sub n equals a sub 1 times 1 minus r to the n divided by 1 minus r. Well, they want us to find s sub 6. Okay, so equals a sub 1 is 4, 1 minus r is 2. Whoops, a little too quick there. Oh my, we already saw that. 4 times 1 minus 2 raised to the nth power 6, because of that number right there, all right? Close that off, and then 1 minus 2 on the bottom. And now we can plug this whole thing into the calculator. Four times 1 minus 2 raised to the 6th power. Close that off, bump to the bottom, 1 minus 2. 252. Is the sum of the first 6 terms of this geometric sequence right here. Okay, so this is number 29. It's going to work the exact same way as number 28, right? We're being asked to find the sum of the first 20 terms. That's what this means right here. We know a sub 1 is 6 and r is 2 because we can read an explicit formula of a geometric sequence. So let's plug all this in. Our formula starts out a sub 1 times 1 minus r raised to the, I keep forgetting that, raised to the nth power, which is 20, all over 1 minus r. And now we can plug that into the calculator. So I'm just going to bring this back up, and I'm going to edit it. This becomes a 20, and this was a 6, right? Just get out there and enter. 6,291,450. 6,291,450. Big number, but that makes sense to us if we apply some math logic here. We're starting with the number 6, we're multiplying it by 2 every time, and we're finding the sum of the first 20 terms. So we would imagine that this number would be a big number. All right, so number 31 is a good one to go over because there's a wrinkle in the explicit formula, in understanding the explicit formula. So let's real quick, a sub n equals a sub 1 times r raised to the n minus 1. That's the explicit formula of a geometric sequence, right? The number out in front is a sub 1, and the number that's being raised to the power n minus 1 is r. Yeah, so when we look at this explicit formula here, the number being raised to the power n minus 1 is negative 4. So the common ratio here is negative 4. Now, what number is out in front? A 1. So a sub 1 equals 1. So that we have to be able to read an explicit formula, right? We have to be able to get that information out of that notation. So now we're finding the sum of the first 12 terms. So s sub 12 equals a sub 1 times 1 minus r raised to the n power. Notice I put that in parentheses because it's a negative 4. All over 1 minus r. Now here I don't need to put it in parentheses because it's not being raised to a power. So now we can plug that. Oh, I keep doing that. The n is 12. 12. Right? Now I can plug it into the calculator. Let's see if I can remember all of this. I'm just going to start from the beginning here. So 1 a sub 1 was 1. So I have 1 times 1 minus, in parentheses, negative 4 raised to the 12th power. Then 1 minus negative 4 on the bottom. Negative, let's see, what is that? 3,355,443. Interesting. Negative 3,355,443. Huh. Okay. Now let me just apply some math logic here. We started with the number 1, and we're multiplying by negative 4 every time. So this number would alternate between positive and negative, but get bigger also, right? So I think I like this answer. I'm okay with that. All right, so number 36 says the sum of a geometric series is 31.75. So right off the bat, I know that I'm starting with the formula for a geometric series, which is all of that. And they're telling me that the sum is 31.75, so I'm going to put that in for S sub n. So we have 31.75 equals, and then they go on to tell me the first term of the series is 16, so I'll put that in for A sub 1, then 1 minus, and then they tell me that the common ratio is 0.5. And they're asking me how many terms are in the series. So that means n. I'm going to have to find that n. 1 minus 0.5 on the bottom. So I have this formula. The only unknown is the n. I have to solve for the n, right? So I know I'm going to have to use some logarithms because that n is an exponent. And that's the only way I can solve for a variable that's an exponent is with logarithms. So let's start this thing out. I know this is just 0.5, right? 1 minus 0.5 is 0.5. So I'm going to start out multiplying both sides by 0.5 times 0.5 times 0.5. And that's so that I can cancel this out with that. Now, 0.5 times 31.75. 15.875. 15.875 now equals 16 times 1 minus 0.5 raised to the n. All right, next step, I need to undo this multiplication by 16. So let's divide both sides by 16. Divided by 16. 0.99219, I'll call it. 0.99219. 0.99219 equals, those canceled out, 1 minus 0.5 raised to the nth power. Next thing, I'm going to subtract this 1 over to the other side. So I have, let me go back here, 0.99219. Since I rounded, I'm not going to reuse that answer. Minus 1. Negative 0.00781. Negative 0.00781 equals negative 0.5 raised to the n. Now I almost have that isolated, the 0.5 to the n, but I have the negatives here. Let's get rid of these by dividing both sides by negative 1. So now this is positive, and this is positive. Whew. Now I can apply logarithms, finally. I could take the log of both sides, or I could just convert it from an exponential equation that it is now to a logarithmic equation. The exponential base is 0.5, so the log base is 0.5 of 0.00781 equals n. And now I can plug that into my calculator with the log base function. Math, log base, 0.5. Yeah. Oh. .00781. Bump out there. And it's probably just 7, right? Because I did some rounding. So the exact answer is probably 7, but we can say n equals 7.0. And we could check that if we wanted to. We could go back to the beginning, plug in 7 for n, and see if we get 31.75. And I'll tell you, you do. So 7 is the exact answer.